Thank you everyone for being here. I mean, the talk is maybe, I don't know if it's a bit late for everyone, but hopefully it will be okay. Just before I start, so I want to thank the organizer for giving me the chance to talk today. So my plan for today is to talk about some of the work that I've completed during my PhD. So specifically, I'm talking about using Friedrichs conformal field equations and using this to study asymptotic charges on vacuum spacetime. So this talk is based on 3 of my papers. 2 of them are already published. 1 is still a preprint, so anything I talk about this paper, as a disclaimer, for now it's not published yet, so just to let you know. So one of the paper was, we looked at the asymptotic charges associated with spin 1 and spin 2 field, and this was in collaboration with my PhD supervisor, Juan Valente Kroon. Then we generalized this to full GR with our co-author Kartik Prabhu. And then more recently, since I moved to Technico in Lisbon, I've looked at spin 0 asymptotic charges on n-dimensional Minkowski spacetime, and this was in collaboration with Edgar Gasperin and Philip Mina. So just as a warm-up, so I'm sure everyone knows what are asymptotic charges, but I just want to start, I guess, from this point. So when we talk about asymptotic charges, we usually refer to some conserved quantities that are associated with certain symmetries. And generally in GR, we don't discuss symmetries in a global sense, but we only discuss it in the asymptotic limit. But since we have different asymptotic regions, that means we have different approaches to study asymptotic symmetries and charges. So this was kind of talked about in Jörg's talk in the morning. But for example, if you want to discuss conserved quantities at spatial infinity, you can take general spacetime and you consider some foliations of constant time t. Then you can write your general spacetime metric in this form. So this is just a 3+1 decomposition of the spacetime metric, where in the expression here we have n is a lapse function and ni is a shift vector. Then you can take one of these hypersurfaces, constant t slices, and you can assume that you have just one asymptotic n. Then on this hypersurface, you can define these notions of ADM energy, momentum, and angular momentum, which corresponds to invariance of the background metric under time translation, spatial translations, and rotations. But these definitions, as you may know, these were originally derived using a coordinate-based Hamiltonian formulation of GR, but we also have similar notions of conserved quantities that were derived using the covariant formulation of Ashtaker and Hansen. And what we actually now know is that we have this infinite dimensional symmetry group at spatial infinity, which is sometimes called the SPI group, and we would expect that we have an infinite number of conserved quantities associated with this group. Originally, the boundary condition that were put to derive these ADM conserved quantities were too restrictive, which led to the reduction of the symmetries from infinite dimension to finite dimension. And what I guess want to point out here is that this symmetry group have a structure very similar to the symmetry group that we have at null infinity, which is the BMS group. So specifically, it's written as a semi-direct product of the supertranslation group with the Lorentz group. The difference is at null infinity, the BMS asymptotic charges that are associated with the symmetry are generally not conserved because we have a net flux that is going through null infinity. And we also didn't have a general definition of asymptotic charges for a long time, so this was kind of pointed out in Simon's talk last week, and at least until the work of Walden Zubel. Okay? Okay, so now what I want to do is I want to connect with conformal geometry. So as I mentioned, the original definition of conserved quantities were kind of based on a coordinate-based formulation, both at spatial infinity and at null infinity, but this was later followed on by more geometrical approach to asymptotic symmetries, which was inspired by Penrose's conformal methods, which turned out to be quite powerful in studying asymptotics. And what will be specifically relevant for the talk is this notion of asymptotic flatness. And similar to how we have different definition of asymptotic charges, depending on the asymptotic region we're considering, we also have different notion of asymptotic flatness. So, but what would be relevant for the talk is this notion of asymptotic flatness at null infinity. And for these spacetimes, you have that the conformal boundary of these spacetime will be, at least at the null infinity, will be similar to Minkowski. And specifically, we will have two disjoint sets of null infinity, which is past null infinity and future null infinity. And the rest of the talk will be kind of focused on this, proving this conjecture by Strominger that said that the BMS group at past null infinity and the BMS group at future null infinity can be related by imposing certain boundary condition at spatial infinity. And if you relate these two symmetry groups, what we would have is you would have, if you have some incoming flux associated with some BMS minus charge at past null infinity, this would be equal to the outgoing flux associated with the corresponding BMS plus charge at future null infinity. And this leads to this identifying this global diagonal asymptotic symmetry group, which we write as a BMS plus cross BMS minus. And this, I guess, identifying of the symmetry group is also relevant for this proposed relation between asymptotic symmetry and a soft gravitational theorem and gravitational memory, which is usually, I guess, shown by this diagram, which is known as the infrared triangle. So before I started working on this, the matching between asymptotic charges was already verified in different settings. The difference between previous work and my work is that I'm looking at this problem from an initial value problem perspective. So, and as you will see, I guess by the end of the talk, is that this recasts this relation between the asymptotic charges as a direct consequence of some regularity conditions on the initial data rather than the boundary conditions that are usually imposed when you're trying to find these relations. But regardless of which approach you take, the main idea is that what you have some definition of asymptotic charges at null infinity, then you want to take the limit to spatial infinity in order to relate these. And this is problematic because the spatial infinity, the conformal structure of spatial infinity is singular, specifically for spacetimes with non-vanishing ADM mass. So usually for all of these, I guess, analysis, you have to use a different formulation of spatial infinity. So for example, in Kartik-Prabhu's work, Ashtikar and Hansen formulation was used. So rather than looking at spatial infinity in this, I guess, Penrose compactification, you look at the space of direction from which you can approach spatial infinity, and this gives you this hyperboloid at spatial infinity, which I think you mentioned. But well, I guess for our talk, what we will doing is we're looking at this using Friedrich's formulation. And I guess the simplest way to look at this construction of Friedrich's cylinder at spatial infinity is to look at it at Minkowski spacetime. Usually you can arrive at this construction of the cylinder by looking at solutions of conformal GD6, but on Minkowski spacetime you can arrive at this just using a simple coordinate transformation and a conformal transformation. And what you get is you get this conformal metric, which is related to the physical metric by this conformal factor theta. Then you get this expression of the metric written in terms of your new coordinates. Then what you do is you define a conformal extension, so you include the boundary point, and the conformal boundary in this case is just given by the condition that theta is equal to 0. Then you can divide this conformal boundary into different sets. So you have just the standard future and past null infinity. Then you have the cylinder at spatial infinity, which is given by the condition that rho is equal to 0. Then you also have the critical sets are given by rho equal to 0 and tau equal to plus or minus 1. And just to like visualize this, I guess, construction of the conformal boundary, if you look at the spacetime metric, you will find that the cylinder, which at rho equals 0, is at infinity with respect to this conformal metric, but the intrinsic metric on this set is well defined, and it's given by the cylindrical metric Q. So what you have now is, rather than having spatial infinity represented by a point, similar to what we have in, I guess, Penrose compactification, you have this blow-up of spatial infinity through a cylinder that connects with Scri minus and Scri plus at the sets I minus and I plus. And when I talk about the matching of asymptotic charges, what I mean is, I want to evaluate the charges at I minus and I plus and hopefully find a relation between the two. So just before moving on to talk about this in a full GR setting, what I want to do is I want to first look at the application of what we've done using this, specifically looking at the spin-zero asymptotic charges. So specifically, so as I said, we've looked at the spin-zero field, and we want to find the asymptotic charges at the critical sets associated with this, but we've looked at it in n-dimensional Minkowski spacetime. So what we do is we do a generalization of this, I guess, conformal transformation that we do on 4 dimensions. And specifically, we define some conformal manifold M with a conformal metric eta related to the eta tilde, which is a physical metric in this way. The theta is just similar to what you have before. But now we also have we define this conformal scalar field related to the physical field in this way. And you can show that this also satisfies the wave equation. Okay? And what we want to do now is we want to use, look at the solution for this equation given some initial data, and then we look also at the charges. And the charges associated with the spin-zero field, you can come, I guess, with this if you look at the Poincare transformations acting on the asymptotic expansion of your scalar field. And specifically, they're written as charges on your null infinity. So they're written as an integral over some cut of null infinity that involve this function here, which is just a function of the angles. And then it also includes the leading order term in the asymptotic expansion of phi tilde. Then, as I said, we want to do is we want to evaluate this at the critical sets. So the way we do this, as I said, we look at solutions to our equation. And to do this, we start with this ansatz for our scalar fields. So we expand in terms of spherical harmonics with coefficients that depend on tau. No, it's at null infinity. At null infinity. Cut of null infinity. Yeah. So then, what you do if you take this ansatz and you substitute in your wave equation, you get this second order ODE, which is just a Legendre differential equation. And what we find is that the solution for this equation depends on the dimension of the spacetime. Specifically, in 4 dimensions, we have 2 solutions. One solution which is going to be regular at the critical sets. The other one will have logarithmic divergence at the critical sets, which can be removed by fine-tuning the initial data. Then on spacetimes where are not 4-dimensional, what you find is you find 2 polyhomogeneous solutions except for finite value of the harmonic L. Okay, so then that gives us this result here, is that the spin-zero asymptotic charges are not well defined at the critical sets unless the initial data for the wave equation satisfy extra regularity condition. And if you assume that your function, which is in the definition of the charges, just you take it for simplicity as a spherical harmonic, and if you take initial data which satisfy these regularity conditions, then the spin-zero asymptotic charges satisfy the following. So for n equal to 4, you will have infinitely many asymptotic charges that will be well defined at the critical sets. And these charges will be fully expressed at the critical sets in terms of the initial data. And finally, you have the relation between the charges coming as a direct consequence of your regularity condition. For n not equal to 4, you will have only a finite number of non-trivial charges for each n that remain regular at the critical sets. And one of these, I guess, finite number of charges will always correspond to the L equals 0 harmonic. Okay? So hopefully this is clear. So now what I want to do now is I want to move on to the full GR case. And in order to do this, I will have to introduce some of the technical aspects, which is to talk about Friedrich's conformal field equation and the regular initial value problem for these equations. So, sorry? No, it's just the dimension of the space.
Oh, the dimension.
Yeah. So what I will do is just talk very briefly about Friedrich's conformal field equation. Then I will also talk about the initial data that we consider in our analysis. And then I will talk about how we generalize this cylinder of Friedrich's to asymptotically flat spacetime. Then about how we use this solution to the conformal field equation to study the BMS asymptotic charges. So simply, I guess speaking, you can just think of the conformal field equation as an equivalent of the Einstein field equation, but they're written on a conformal manifold. So in our work, you can just start with the four-dimensional Lorentzian vacuum spacetime. So that means your Ricci tensor satisfies this equation. Then you introduce a manifold M and G and a map from M tilde to M such that the pullback of G is related to G tilde in this way. So here, Xi is just our conformal factor. This will give you some relation between the unphysical Ricci tensor and the physical Ricci tensor. And you would want, obviously, if you want to look at the, maybe, for example, the asymptotic charge at the conformal boundary, you want to solve for your unphysical field, but this equation is singular at the conformal boundary, which means we can't solve it. So the idea of, I guess, introducing the conformal field equation is you want to introduce equations which are regular at the conformal boundary. And the way to do this, Friedrichs, I guess, introduce new variables and rewrite these equations to arrive at the conformal field equations. So I cannot obviously go through the derivation of these equations, but what we get at the end, as I said, is a set of equations which are regular at the conformal boundary. And in our work, we're specifically interested in a form of these equations which have an extra gauge freedom in addition to the conformal gauge freedom that you have in your equation. And this extra gauge freedom comes about when we write our equations in terms of a Weyl connection, which is defined in terms of this one form Fa. Then what you get is this set of equations which we call the extended conformal field equation. And these equations are written for some orthonormal frame with respect to the conformal metric. And then there's this P and rho, which are just the geometric and algebraic curvature, which are written in terms of the connection coefficient associated with the Weyl connection. We also have the L, which is just a Schouten tensor associated with the Weyl connection. And finally, we have the rescaled Weyl tensor, which is just the Weyl tensor multiplied by the conformal factor to the power of -1. So if you were to expand these equations in terms of local coordinates, what you would get is you get some PDEs that you can solve for the frame, for the connection coefficient, the components of the Schouten tensor, and the rescaled Weyl tensor. But what you will see from this equation is that you don't have an equation that can fix the conformal factor and also the one form Fa. So this is, as I said, the gauge freedom that we have. And luckily, Friedrichs formulation also includes a choice of gauge, which we call the F gauge, which allow you to fix this one form and the conformal factor. But this choice of gauge has to satisfy these supplementary equation, which you can think of as just some constraints on the initial hypersurface. And I guess the most important thing, I guess, to take away from this is that if you have a solution to the extended conformal field equation, and if you have a choice of gauge which satisfies the supplementary equation, then you automatically got a solution for the vacuum Einstein field equation on an open set where Xi is not equal to 0, meaning on the interior of your manifold.
What is this S?
So this is just written in terms of the metric. I don't know what, I don't think there's a name for it, but it's just written in terms of canonical delta and the metrics, basically. And
oh, I see.
So, yeah. Okay. Okay, so in our work, what we do, we also expand these equations in terms of spinors in order to scalarize these equations. So I just want to maybe talk about this maybe on the board very quickly. It's not going to be for long. I mean, I'm pretty sure everyone is familiar with this. So for example, let's take the one form. So this is one of the, I guess, unknowns in our equations. So we have like the one form Fa. You can write this, obviously, in terms of spinor as just F A prime. Then what we want to do is we want to do a kind of a 3+1 decomposition of this, and we do this in terms of spinor by using something called space spinors. So if you take, for example, some hypersurface, and you consider you have some norm tau A, this can be written in spinors, it's just tau A prime. Then you can get the space spinor version of this spinor by just contraction of this with this norm. So you can just write it as tau A, and then And then you symmetrize over the two indices AB, and you get this FAB. And you can show that this symmetric spinor in the two indices have three independent components, which represent a three-dimensional vector. Okay, so as I said, I'm pretty sure everyone is familiar with this. But then after that, we take some spin dyad. So what we do, we consider two spin dyads. So we have, for example, A here. And we write something called the primary spinors. This is, again, just part of Friedrich's formulation. So we define XAB, which is just some symmetrized, combination of these spin dyads. So we just write it as A, and there's some factors here for the normalization, and you do that for the Y. You also have A, and then this will be the 1, 1, and then the Z. And then from there, so this is, as I said, just a symmetrized components of the spin dyad. Then from there, you can just break up your FAB as a component of this. So you can just write it as FAB can be written as Fx XAB plus Fy YAB plus Fz ZAB. Okay? So this is what we do for two spinor indices, but we can also do this for four spinor indices. And so basically this is kind of like, I'm not going to go through everything, but I mean, what we get is just we break these background fields into these spinor fields. And then for the rescaled Weyl tensor, we break it into the rescaled Weyl spinor. Then, as I said, we decompose this in terms of these spin dyads. And then what you get at the end is you get these 45 equations, or 45 components of your background field satisfying 45 equations. And then for the gravitational field, you have these 5 components which satisfy 5 evolution and 3 constraint equations. Okay, so now that we have these equations, in order to look for solutions to this, I also want to talk a bit about the initial data that we use in our analysis. So the initial data, the specific initial data that we use fall under this general category of initial data which are asymptotically Euclidean irregular. So you say that a 3-dimensional Riemannian manifold is asymptotically Euclidean irregular if there is a 3-dimensional compact manifold, S and H, where you have some points ik on S and some function omega, and a map from phi from S, minus the point to S tilde such that the omega satisfy this condition. And this condition roughly tells you that the points ik are on the conformal boundary of the manifold, and that all the other points are on the interior of the manifold, and that there is a conformal relation between H and H tilde. So it's just what, just easily the way to see it. Then the specific class of initial data that we use is this initial data which was introduced by Wang in 2012. So this is initial data on the vacuum, on the physical manifold. So it's a vacuum initial data set, which is written as just some asymptotic expansion in terms of this radial coordinate r. And it's written in terms of these two functions, xi and zeta, which are functions on S2, and also in terms of these two constants, a and b. But these are, as I said, so these are initial data on the physical manifold. What we want to do is now we want to transform this to our conformal manifold. So the first thing we do is we consider some inverse coordinate transformation. If you use this in your expression of the metric, what you can find is you will find a kind of a natural choice of the conformal factor. So what we do, we introduce this S prime, which is just a 3-dimensional compact manifold with one spatial infinity point I and a map from S prime minus I to S tilde. And then we introduce the conformal metric H prime with the conformal factor given by this form here, written in terms of this curly row, which is just the norm of the inverse coordinates. So then, because we are doing calculation with this initial data, we wanted to basically avoid doing as much calculation as possible. So what we did is first we introduced our normal coordinates, and these normal coordinates are introduced such that the first order derivative of your metric is equal to 0. Then we exploit the conformal gauge freedom, so we introduce another conformal metric, h bar, and we choose our conformal factor such that the second order derivative of our metric is equal to 0. What this gives us, so this extra conformal rescaling here, means that our conformal factor, omega prime, goes to omega. And this omega can be Taylor expanded around rho equal to 0. So rho equal to 0 is just the spatial infinity point. And in this expansion, you have this coefficient of rho to the power 3, which I write as a pi 3 omega. And this will be very important when we're talking about the asymptotic charges. So this is related to the Huang's initial data. So it's written in terms of the function xi and the constant a. And what you get from doing this, I guess, conformal transformation, you get this initial data, which, as I said, have a simpler form that we can deal with in the calculation easily. So specifically, the metric to 0 order is just the Euclidean metric, and then all the higher order terms vanishes up to the order of rho to the power 3. Then if you use this initial data in your constraint equation, you find the following. You find that your components of the Skoughton tensor, the electric and magnetic part of the rescaled Weil tensor, will be singular at spatial infinity. So this is kind of, again, the problem of spatial infinity manifested at the level of the initial data. So in order to remove this singular behavior, what we need to do, we just follow Friedrich's footstep. So we just introduce another I guess, conformal factor of order of O rho. Then if you do this conformal transformation, you get the following. So your components of the metric remain the same, but then you get initial data, which are all regular at spatial infinity. So now that we have initial data which are regular, what we can do is, as I said, look at the solutions. But in order to do that, I also want to briefly just talk about how we construct this F-gauge, or how we can resolve this problem of the, I guess, the singularity of spatial infinity at the level of the equations that we have and the space-time, not just at the level of the initial data. And the way we did this in Minkowski is that we did this blow-up of the spatial infinity point to a cylinder. So we want to kind of do something similar. And now we have a spatial infinity point, I. Usually what you can do is you can replace the point I with the space of directions at I, and this gives you a blow-up of the point I. But in our work, what we do is we replace I with a subset of the bundle of normalized spin frame with structure group SU2C. So that means that the blow-up, rather than having a blow-up which is diffeomorphic to S2, we have our blow-up is diffeomorphic to S3, and its quotient by U1 is diffeomorphic to S2. And you can think of this extra dimension in Friedrich's blow-up as reflecting the freedom in choosing the phase parameter of your spin frame at the point I. So, and more specifically, in order, I guess, to define this F-gauge, what we do is the following. And again, I think this was talked about in your talk in the morning. So what you do is you can you have the point I, which is spatial infinity. You choose a spin frame at I. Then you take an element of SU2C, and then you can write a transformed spin frame in this way. Then we want to extend this spin frame in a neighborhood of spatial infinity. And the way we do this, so we take some open ball with radius A centered at I, and then we extended the spin frame by parallel propagation along geodesic starting at I. So if you have your rho to be the affine parameter along the geodesics, you can write your the spin frame on the open ball are just epsilon A rho t. So now we have some spin frame in a neighborhood of spatial infinity at the initial hypersurface. We want to take this off the initial hypersurface. And the way we do this, we consider conformal geodesics which are orthogonal to the initial hypersurface, and then we propagate our spin frame along these conformal geodesics. So then if we have your tau to be the parameter along the geodesics, then you can write your spin frame on the spacetime as just epsilon A tau rho t. Then in our work, rather than working with a four-dimensional manifold, which you can think of as the evolution of the initial data that we mentioned. We work with this five-dimensional manifold with coordinates tau, rho, and t. And on this five-dimensional manifold, you have some the conformal boundary, which are defined by the condition that rho is equal to 0 and tau equal to plus or minus omega over kappa. And this omega is just some function that is taken to be smooth and non-negative, and it satisfies the condition that omega over kappa goes to 1 as rho goes to 0. And you can think of this omega as just an extra gauge freedom in this in Friedrich's construction. Then on a conformal boundary, we can define similar subsets to what we had in Minkowski. So we just have the past and future null infinity, we have the cylinder, and we also have the critical sets. So obviously, these gauge conditions that we have in like the Friedrich gauge, I guess part of the formulation is that we encode these gauge conditions in the initial data and also in the properties of the field that appear in the conformal field equations. And from there, we have like I guess 3 good things that we get from that. So the first thing is, so as I said, initially we didn't have an equation to fix the one form and a conformal factor. And if you use this F gauge, what you get is you get that these fields are written in terms of the initial data. So without solving your field equation, you have these things are known a priori. Then also in this F gauge, we have that our extended conformal field equation reduced to a symmetric hyperbolic system where the evolution equations are written as a transport system along these conformal JD6. So that means that rather than what we started with some PDEs that we need to solve. Now we just have some ODEs that we need to solve along the conformal JD6. Okay, so now I think most of the technical aspects of the, I guess, the analysis I introduced. So what I want to do now is I want to give a simple statement of the results that we have, specifically for the BMS asymptotic charges. And then I will talk about how we get there using everything that I've talked about. So the main results read as follow, that for Huang's initial data, the asymptotic BMS charges are not defined at the critical set unless the initial data satisfy a certain regularity condition. And if you choose the initial data to satisfy the extra regularity condition, the BMS charges at the critical sets will be fully written in terms of the initial data. And the matching of the charge follows directly from these regularity conditions. Okay, so in order to do that, first what I want to do is I want to briefly just talk about the definition of the BMS asymptotic charges. So these charges are usually defined, as I said, also at null infinity, and they're associated with some function on S2. So for each function, we define a charge, and these are written in terms of these 2 terms. So one term, which is related to this phi2 component of the rescaled Weil-Sminner, and then another term, which is just a shear tensor contracted with a News tensor. And this, I guess in our work, what we want to do is we want to express this charges in terms of scalar fields. So you can actually write this in terms of scalar field, but it depends on whether you're working at past null infinity or future null infinity. So for example, at future null infinity, you can write it in terms of this sigma and mu and gamma, which are just some of the components of the spin connection coefficient. And if you, I guess, notice here, I have this bullet notation just to indicate that this expression of the charges, it is written in terms of a different gauge than the one that we're using to solve the equation. So it's written in terms of the Newman-Penrose gauge, which means that these are just the Newman-Penrose connection coefficients. Okay, but now if we want to evaluate this at the critical sets, we have to transform this expression of the charge from the Newman-Penrose gauge to the F gauge. And the way to do this generally is you take your components of the metric, you take components in the Newman-Penrose gauge. Its component in the F gauge will be related by this here, which theta is just some conformal factor. This will imply a transformation between the Newman-Penrose spin frame and the F gauge spin frame, which is parametrized by this conformal factor and this transformation matrix, which is just an SL2C matrix. And the main idea, I guess, if you want to get explicit transformations to this, what you do is you do an asymptotic expansions for the conformal factor and these transformation matrices. So this was originally done in a paper by Friedrich and Kanner. So what we do in our work, we just follow a similar, analysis to this. And what we find is the following. So we find that the term, which is associated with the background fields, will vanish at the cylinder, at basically spatial infinity. And we also find that the Newman-Penrose component, the phi2 component, is just equivalent to the zero order of the phi2 solution in the F-gauge. So that means that if we want to evaluate our BMS charges at the critical set, we only need to consider a solution to the phi2 component of the air-scaled Weyl spinner. And the way we do this is we do something similar to what we've done in a spin zero case. So as I mentioned, in this case, we're working on a 5-dimensional manifold. So what we do is we expand our these FIMs in terms of this C function, which is just a function of SU to C. So these are related to the standard spin-weighted spherical harmonics on S2. And then we have these coefficients in terms of the coordinate time tau. If you substitute this in the equations for the scaled Weyl spinner, you get some first-order ODEs that you can solve for A2. But then in this case, I also want to do some kind of similar decomposition of our initial data. So we had this by 3 of omega. So again, what I do, I decompose it in terms of this C with coefficients that I write it the same, but with just some subscript of 2L m plus L. Then what I find is that the solution for A2 is, so specifically for L equals 0, it's just a constant, which is related to the coefficient here, which is L equals 0, m equals 0. And then for L equal 1, I have this as just a linear function of tau, which again depend on the initial data. But then for L bigger than or equal to 2, we have the following. We have that the solution for phi 2 is going to be written in terms of Legendre polynomials of order L, and Legendre function of the second kind of order L. And we have these two constant ALM and BLM, which can be expressed in terms of the initial data. And the main thing here is that similar to what we kind of had in the 4-dimensional case on Minkowski for the spin zero field, we also have some logarithmic divergence specifically coming from this QL. So that means if we want this solution of A2 to be regular at tau equal to plus or minus 1, we need to impose a condition that this BLM is equal to 0. So imposing this will also put some conditions on our initial data. So specifically, we find that the solution for the phi 2 is going to be regular at tau equal to plus or minus 1, if and only if the coefficients all vanish for all odd harmonics bigger than or equal to 2. And since this pi 3 of omega was also related to the physical initial data, specifically the function xi and the constant a, we can also put this condition on the physical data. So what we do, I also do some decomposition or kind of expansion similar to this one for the function xi. And what I find is that the regularity condition are just, again, we require the coefficient of the expansion to be 0 for all odd harmonics bigger than or equal to 2. So then, I guess, putting this all together, what we get at the end is the following. So we get that if you have some initial data that satisfy the extra regularity condition, and only if you have that, you will have your charges at critical sets will be well defined, and you can write all of them in terms of your initial data. We also get that the relation between the charges at I plus and I minus follow directly, so you have that the charges at I plus are equal to the charges at I minus multiplied just by the factor of minus 1 to the power of L. Okay, so this is, I guess, the main result. So I just want to maybe talk a bit about some of the, I guess, the conclusions from this. So as I said, like the difference between what I've done and previous work is that we kind of recasted this problem or the matching between the charges in terms of initial data rather than the antipodal boundary conditions that are usually required in order to obtain this relation. And the interesting thing is that, so as I said, we've looked at the asymptotic charges associated with spin 1 and spin 2 fields, and we can kind of get a comparison between the linear field and what we have in full GR. And specifically in spin 2 fields, we have the result is kind of not really the same as what we have here. Specifically, so as you see here, for all harmonics bigger than or equal to 2, we have that the charges, half of them will vanish. And this is not really the case in spin 2 field. We don't have this vanishing of the charges. And I guess I don't have like an interpretation of this, but at least you know, Juan just interprets it as like the full GR is like more restrictive, and the constraints in this case are more restrictive than the spin 2 case. So I guess this is one thing. The other thing that I want to mention as well is that I guess it was mentioned maybe that for the Cristoballo and Kleiman initial data, this matching between the BMS asymptotic charges should follow. But it was, I think, argued maybe non-formally by Ashtaker that for these class of initial data, all the non-trivial charges will vanish. And in a way, the results that we have kind of give this formally, because we can just compare the Cristoballo and Kleiman initial data to our initial data, and we find that for them, the xi is equal to 0, which directly gives us that all the charges except for the L equal to 0 will vanish, and that means that in this case we will have basically just the trivial charges for L equal to 0. The last thing is like maybe just comment about some future work. So we were kind of inspired by some paper by York about the gravitational memory, which kind of talks about the relation between the gravitational memory and characteristic initial data. And since here we're doing kind of something, we're looking at the asymptotic charges, and we're trying to relate this to data on a Cauchy hypersurface. So we're also trying now to look at what is the relation between gravitational memory and initial data on a Cauchy hypersurface. And this, in a way, is more complicated than what I have, because for the asymptotic charges, we only require the zero-order solution of the conformal field equations. In order to look at this gravitational memory, we're looking at the shear, which involve looking at first-order and second-order solution of these equations. So this is a project which I'm kind of stuck with at the moment. So this is one thing. Then the next thing that I'm stuck with is that, okay, I thought this is too complicated. Let's look at the simpler case. There is definitions of electromagnetic memory, and there's a scalar memory. Maybe we can look at this in a linear case and see if we can relate this to also initial data on a Cauchy hypersurface. And I think, at least for now, the problem for me is more conceptually. I think I don't understand exactly what are these things. So maybe my problem is more to read on them and see how, I guess, if this even conceptually is possible. And that's it for me.
We have 15 minutes for the question.
Oh, wow, okay.
So I guess in the talk I gave, we had these. Well, I can't expect you to remember it. But if you took sine Lawson and you took its expansion into the space time, you had all these quantities which gave these higher charges to describe. One of the things that would be a great one to understand would be whether you could give them an interpretation of space-time infinity. So I suppose really the question is, how good would your machine be for comparing data as u goes to minus infinity and describe with data at I0?
Can you say again? So the data at, sorry.
Well, so I guess the point is that those cues that I had for these higher charges were part of the, they could be read off from the fall-off.
Yes.
Of the bulk curvature components as you go into space-time. And as you go further and further into space-time, past the fall-off as you go to try, then you have to read off more components. But yeah, so the question then is, could your machinery give you expression for those same quantities? See how they could be represented spatial affinity in terms of fall off of the, and the sort of thing you might expect is that these seem to be multiple elements or something. Yeah. So then, could your machinery line up?
I think so. I mean,
the order is in 1 over R.
Yeah. So I mean, this is I think this is kind of related, because I remember I actually looked at the expression that you had, and I thought this is something that would be interesting to see. Like, because I mean, it would be And I think some of them also is related to the shear, I think, but I'm not really sure. But
well, yes, but I mean, I guess as you come out, as you come out, sure.
so, and what I'm saying is, so I'm saying with gravitational memory, we kind of, like as I said, rely on kind of maybe leading order things, not exactly leading order, but then, so maybe, sub-leading order terms. In our, when we're looking, I mean, as I said, the complication is more like if we're able to solve the equation. The equations, obviously, as I said, they're very complicated, and so we have like these 45 equations, and when you're looking at zero order, things just like simplify. But then even when you look at first order, it's not always clear. So I think some of the calculation that I'm doing, I'm able to kind of decouple some of the equations, but I don't know if I'll be able to solve for everything, for example, even at first order, analytically at least, I don't know.
Another question that's very naive or long shot. So we were talking about this Penrose's property yesterday, which tells you about how poles connect square lines like plus, and then with positive ADM mass holds in dimension 4, but doesn't go higher.
Yeah.
So you're saying that in dimension 4, you do have infinitely many charges, but higher or infinite.
Yeah.
Is that possible?
Yeah, I mean, to be honest, again, this was very interesting for me, and I think, I mean, because to be fair, I was surprised with the result in dimension not 4 initially, because I didn't really expect anything. And there's also this thing, I think, for example, when people looking at scalar memory, there's this differentiation between even dimension and odd dimension. And I expected to kind of find something similar. Okay, when you go to dimension, higher dimension, you will find something different between the two, but it's not just gonna all be kind of similar. But yeah, I think it could be related. And that's why I think I was also kind of talking to you about this, but yeah, so.
This isn't my question, but what happens in lower dimensions?
Sorry, so I think our equation, so the thing that we have for a spin zero field, I don't think, the problem in lower dimension is just more the construction itself. I don't really know if, obviously we need to have some time, I don't know how to construct the cylinder in lower dimension, because what we did, we just did a naive thing. It's just like, rather than having like the cylinder as just R S2, we just said, okay, it's just R Sn minus 2, right? And I just don't know if in like dimensions less than 4, I mean, it's fine. I think you can do it in 3, but I don't know for, yeah, I don't know about this, yeah.
My real question was, so this F gauge thing you're talking about, where you go up and one dimension. So you're saying that turns the problem into ODEs, is that really main reason?
I think what,
what's the real reason?
yeah, I think the main reason is we're doing, like, using this F gauge. I think it more depends on, like, doing this conformal GD6 and using the properties of conformal GD6. And in a way, this simplifies the equation. To be honest, like, these calculations I've never done before. I just trusted Friedrich, and we're like, okay, these things simplify, and hopefully it'll be fine. And I have, like, some, like, Mathematica notebook, and it's like, I think Juan have it, and you're just like, you know, all of things PD, and then it kind of magically become OD. Once you, it's like, I think it's more just based on the properties of conformal GD6, but maybe I don't know if you have like more thoughts on this, but yeah.
Well, I would say that not all the terms are ODEs.
Yeah, not all, yes. So
there is one part that remains symmetrical of the system.
Yes, that's the for the file, yeah.
All the other ones become ODEs.
Yeah.
One that describes the gravitational waves that still is symmetric.
And this is just happening over the cylinder, you don't change the dimensions, right?
It's a lot.
Well, I don't know what happens in higher dimensions. I only deal with 4.
No, but with this, you're just doing this on the cylinder.
Yeah, on the cylinder, yes.
Right. And then how do you actually dimensions? Is it firing off?
So again, so I don't do this on Minkowski. Minkowski, we just do the conformal thing, and we don't even use conformal GD6. There's no, I don't think, I mean, we can define F gauge and stuff like that, but it's not even needed. I think on Minkowski.
Well, the metric that you write down for Minkowski is in the F gauge.
Yes.
So Basically, all the construction is done in the metric
Yeah.
that's the metric that pops up.
Yeah.
In the FA.
But it is the extra dimension then down on the slope as well?
I think it's maybe included in the sigma here, which is just the sphere, basically. So, and then that just acts as a Laplacian, and then it just like, it gets like, that's why I guess the dimension comes in the expression that we have here, so for the ODE that we get. You know, but again, I don't do this in full GR. In full GR, I'm just limiting myself to 4 dimension. I think that's enough. So.
Any further questions? Not, let's conclude the day.